right, we're going to go ahead and finish looking at our linear inequalities in one variable. In this presentation, we're going to talk about visually or how to solve inequalities visually using graphs. We're also going to talk about some application problems involving inequalities. All right, so we have, to start us off, we're going to talk about solving linear inequalities graphically. The first thing that we're going to do, and if you recall when we talked about solving equations graphically, there were two methods that we could use for this. We could use the intersection of graphs method, or we could use the x-intercept method. All of these are going to be using the intersection of graphs method. And so what we're going to do is we're going to start by plugging each side or part of the inequality into the graphing calculator for y1, y2, y3 if needed. And then we're going to graph in an appropriate window. In order to do this, we're going to start by just considering it as an equation. And remember that when we solved equations, we found our point of intersection and we kept the x-coordinate. When we talk about inequalities, we're going to add a step onto this, and we want to identify the side or the region that satisfies the inequality statement. So it's going to be similar to, remember when we talked about where is the graph positive, where is it negative. We're going to do something similar to that, but instead of just looking at the x-axis, we can look at a line that is slanted. We can look at a line that is located at y equals 5 or y equals -2. We can actually do all sorts of crazy things here. But it's still going to be kind of the same basic idea. All right, so let's go ahead and jump into some examples. All right, the first example we have is, I'm going to go ahead and give you guys the graph, but these are things that you could easily go ahead and graph in your calculator. The first thing that we want to do is we're going to start by solving the equation. And so for instance here, we want to know where is f of x equal to g of x. Remember that when we do this, we want to keep only the x value. The y value just means that they're equal when x is equal to that number. And so, for instance, when we look at this one, we have f of x is our blue graph, g of x is our red graph, and they intersect at the point 8, 7. And so, when x is 8, then f of x is equal to g of x. F of 8 is equal to 7, g of 8 is equal to 7, and that's our solution. Okay, now, that's always going to be our first part of this. Now, the second part is we're going to look at some inequality statements. And so, when we look at the inequality statement, f of x is less than or equal to g of x. What we're basically looking at here is, I'm going to talk in terms of colors. We have f of x is our blue line. In order to be less than or equal to, we want to be below g of x, which is our red line. And so visually, this is what we're looking for. And so we want to know, okay, where does this happen? Well, this happens when we are to the left of 8. And similarly, like when we talked about our positives and negatives previously, remember that we only want the x values. The y values, that's what we're comparing, but we always want our answer in terms of the x values. And so for this, our answer is going to be x is less than or equal to 8. All right, for the last one on this one, we want to know where is f of x greater than g of x. And so again, we're going to kind of translate this into colors. We have f of x is our blue. In order to be greater than, we want to be above. And then g of x is our red. And so where is the blue line above the red line? Well, that happens when we are to the right of 8. And so here, our answer is going to be x is greater than 8. And notice here that we use the same inequality symbols that we used when in our original statements. If you are confused about do I use x's or do I use y's, always double check your instructions, because if you notice up here, what does it say? Determine the values of x. That means we want x coordinates, and so we're always going to be using these x coordinates that are on our graph. All right, that's the first one. Let's go ahead and look at another one. All right, we're going to look at one that has 3 things going on. And so don't worry about all these things. Remember, just zone in on what it is you need. And so, for instance, here we have, for part A, we want to know where is f of x equal to g of x. And so when we look at this, let's see here, f of x is my red line, and g of x is my blue line. And so to figure out where our red line and our blue line intersect, we are looking at right here. Again, remember that we only want the x value. And so here we get x is equal to 4. We have the point 42, and actually technically it's 4200 on this line. Okay, the next thing that we want is we want to know where is g of x equal to h of x. And so we have our g of x is the blue line again. Our h of x is the green line. We don't care about the red line in this problem. And we want to know where do these 2 lines intersect. And these 2 lines intersect when x is 2. And again, we do have a point of 400 if you just want to kind of identify both of these points. We don't care about the y values. We really only care about the x values. But it doesn't hurt if you write more things out than you need. All right, so now we're going to go ahead and look at example C. We're going to get into our inequalities. And so for our inequalities, this particular picture, we can do 3-part inequalities. We can do 2-part inequalities. It doesn't matter. But what we want for this particular one, for example C, is we want f of x is less than g of x is less than h of x. Okay, so we remember that 3-part inequalities, you have to satisfy all of the conditions. So we want to know what x values do we have red, below, blue, below, green. All right, so let's see what we can do here. Okay, so in order for us to satisfy this, let's see what we can do. We want red below blue. And so when we draw this, red below blue is going to be from our 0 to 4. But we also want blue below green. And so blue below green happens from 2 to 6. And so the result that we want is we want the one that satisfies both of these. And so essentially when we look at this, you can think of this as red below blue and blue below green, or you can also think of this as where is blue between the red and green. And so what we get here is we have our variable. We have that this starts at 2 and it finishes and we're done. And so that's one of the ways that you can think about these three-part inequalities. Just like we said before in the last video, when we talk about three-part inequalities, we are talking about, the middle portion. All right, for part D, we want to know where is g of x greater than or equal to h of x. And so this is going to be blue above green. Now, even though we don't have the full picture on this one, one thing to note is if you look at our previous example, notice it had arrows on the end. And so we could go ahead and use just x is less than or equal to 8 and x is greater than or equal to 8. When I look at the numbers for this one kind of tells me that we are looking at an application problem. And especially since we are only looking in the first coordinate where we are positive, we do want to be careful about that. Notice here that when we look at the endpoints of these lines, we do not have arrows. It is starting at 600. It is ending at 6. And so because we don't have those arrows, we do need to be careful when we write our inequality. This is still going to be a three-part inequality because what we want to do here is, let's set up what we want generally. We want blue above green. And so blue is above green from here to here. And so what we are looking at is, you can say x is less than or equal to 2. But again, because of the way that this is drawn without the arrows, we do need to make sure that we are starting at 0. And so we get 0 is less than or equal to x is less than or equal to 2. Okay, that takes care of our visual representations. And again, as you proceed in math, you can use your calculators to kind of help you out when you do these problems. You can use them as check steps to make sure that you can see visually what's happening and double check your answers. Okay, the last thing that we want to talk about is we want to talk about application problems. Inequalities, this is not something that just exists in, math class, and we didn't invent these things to make you miserable. They do show up in real life. And so when looking at application problems, we do want to think about statements and how they should be translated. When we talk about equations, we do have statements that mean equal signs. We have is equal to, equals. You can also have just the word is by itself. And yields, results in, there's lots of them out there. And we also have the same thing when we talk about application problems. All right, so let's go ahead and look at some words. And again, this is not a comprehensive list, but these are the most common. So we have is greater than, is more than. And so one of the first things that you're going to see when we talk about inequalities is notice that we have this word is in a lot of these. Just like when you see is in regular statements and it means an equal sign, if we add on to that is greater than, is more than, is less than, this is an indicator that we are talking about an inequality statement. Is greater than, is more than. This translates to it's our greater than symbol. And so it is going to be our crocodile mouth opening towards the right. Is less than is going to be the other direction. When we say greater than, more than, less than, these are all examples of strict inequalities. There is no bar underneath. On the other hand, when we see is at least, is at most, these are not strict inequalities. These can be equal to. If I tell you that you need at least $20 to go to the movies, can you go into the movies with $20? Yes, you can. Okay. And so 20 is included in our result. Same thing with minimum and maximum. Minimum, if the minimum score to pass the class is a 70, you can pass the class with a 70 or higher. And then we also have our phrases that interpret into three-part inequalities. If we say is between something and something, this is going to be a strict three-part inequality. If I tell you to go stand between the two trees, you have to stand in between the two trees. You cannot be in the trees or on the trees. You have to be somewhere in between them. On the other hand, if it says something like from to to, this is going to be an or equal to statement. If I say I am driving from my house to school, well then at one point I was at my house and at one point I am at the school, and so they are included. Other phrases that you can see is you can also see sometimes exclusive and inclusive. And this is just to make sure that it is definitely clear in terms of whether these endpoints are excluded or included. And so that's what those two things. If you see exclusive, it is strict inequality. If you see inclusive, you can equal them. All right, that is our terminology. And so now let's go ahead and look at some application problems. Okay, let's see here. Our first example, we have the past and future percentages of the population who are overweight can be estimated by W of x equals x plus 45, where x represents the years after 1980. We want to estimate when this percentage was between 70% and 77%. Okay, so we're going to go ahead and start with our x plus 45. And we have our two values. We have our 70 and our 77. Between, remember that between is exclusive. In order to be between 70 and 77, we cannot equal 70 or 77. And then now that we have our three-part inequality, we can go ahead and solve this. So, in order to solve this three-part inequality to get x by itself, I want to subtract 45 from the middle, from the left, and from the right. And so what we end up with is 25 is less than x is less than 32. It says estimate when this percentage was between. And so we do want to keep in mind the original, what does x represent? X is the years after 1980. And when we answer this question, we do want to go ahead and use words that indicate an inequality. And so it was between, and you can go ahead and use the same terminology that they're using. If we add 25 onto 1980, we get 2005. And if we add 32 to 1980, we get 2012. And if you want, you can also go ahead and add the word exclusive to indicate that 2005 and 2012 are not included in the solution set. All right, let's go ahead and look at the next example. Okay, this next one's going to be a little bit more involved. And so what we have here is we have the altitude increases, or as the altitude increases, both the air temperature and the dew point decrease. As long as the air temperature is greater than the dew point, clouds will not form. And so here we have, we're going to have two equations for this. The first one, it says, typically, the air temperature T cools at 19 degrees for each 1 mile increase in altitude. We also have the dew point, D, decreases by 5.8 degrees Fahrenheit for each 1 mile increase in altitude. All right, so we have two things going on here. So let's start with the air temperature. It says the air temperature at ground level is 65 degrees Fahrenheit, and we want to write a formula for a linear function T that gives the air temperature at X miles high. Okay, so let's see what we got here. We have our starting value. Our starting value is going to be the air temperature at ground level. And so we're going to get T equals 65. And then it says that the air temperature cools at 19 degrees for each 1 mile increase in altitude. And so X is our miles, and so what we're going to do is we're going to subtract 19 x. I'm going to adjust this just a little bit, just to be a little bit more precise. I wrote an equation, but it did say it wants function notation. And so let's go ahead and put it in function notation. Okay, so we have our starting value. Remember that it cools at 19 degrees for each 1 mile increase. This is an indicator that this is our slope because we do have our 2 units. We have it's going down because it says cools, and so that's what we have. All right, for part B, we have, suppose that the dew point at ground level is 50 degrees Fahrenheit, and we want to write a formula for a linear function d that, I'm assuming that's supposed to say views the dew point at x miles high. If you can figure out what word that is, let me know. Okay, so same thing. So we have d of x. We are starting at 50. And it says that it decreases by 5.8 degrees Fahrenheit for each 1 mile increase in altitude. And so same thing here. We have it decreases, it's subtracting. This is our slope because we are have 2 units there. We have our degrees Fahrenheit for each 1 mile increase. And so we should get d of x equals 50 minus 5.8x. All right, these are our 2 equations. And so now we want to go ahead and determine algebraically altitudes where clouds will not form. And so up here it says, as long as the air temperature is greater than the dew point, clouds will not form. And so what we're essentially looking at here is we want t of x is greater than d of x. Here we do want strict inequalities. It does say strictly greater than. It does not say or equal to. And so this is what we're looking at. All right, so we're going to go ahead and begin our expression. T of x, we have 65 minus 19x is greater than 50 minus 5.8x. All right, if we go ahead and solve this, I'm going to move my constants to the left. I'm going to move my variables to the right. That way we have positives. We get 15 is greater than, I want to say 13.2, but I'm going to double check this. Oh, I was right. Okay. 13.2 x, and then we want to divide. I got 1.136. You may be saying, okay, well, that doesn't sound very big. But what we have here is if let's go back and read what we have here. If the altitude is below 1.136 miles, clouds will not form. And if you want, you can actually make this a little bit better. We're going to say 1.136 miles above ground level. And we're done. Okay, so now you can kind of see how we use inequalities in terms of application problems. Okay, that finishes up our inequalities. In the next section, we are going to be looking at solving absolute value equations and inequalities. We're also going to talk about graphing absolute value equations.